Go ahead.
Yes, it's a great pleasure to introduce Professor Jeff M. Sorry how to pronounce his name, but Jeff is easier.
Jeff is fine.
Yeah, so from Swansea and now from Durham University, who will talk about phase transitions and persistent homology. Over to you, Jeff.
Okay, thanks, Vitaly, for inviting me to speak here. It's a pleasure to give this talk. This is my first time giving a talk on this particular project, although Nick Sale, I think, has already given a number of talks on this. So what I'm going to be talking about is joint work with Nick and with Biagio Lucini. So Biagio is a physicist at Swansea, and Nick is our joint PhD student. It's a joint project, but I want to say that Nick has really been fantastic at driving this forward. And he's put Biagio and me in the very pleasant position of just sitting back and watching the project unfold in front of us. It's kind of a dream come true. So Nick is entering his final year of his PhD. So he will be looking for postdoc positions if any of you have anything available. And I'm thinking of you, Heather. Right, so let me start by talking about the world around us. Now, we have some chemists here, and chemists know things are made out of molecules, and molecules are made out of atoms. So here's a kind of a schematic of an atom. You've probably all seen this cartoon picture. We have a nucleus in the middle and some kind of quantum cloud of electrons orbiting around it. Now, these things in the nucleus here, the nucleus is a lump of protons and neutrons for the most part. And there was a question, what are protons and neutrons made out of? When this atomic picture was first put together, people thought that protons and neutrons must be fundamental particles, the point particles like the electron. And then people started to probe them a bit further, and they realized that there's some internal structure. And the story that you've probably, many of you have probably heard, is that protons are made out of these things, protons and neutrons are made out of these things called quarks, which come in different types, and they're bound together by some force called the strong nuclear force, which is transmitted by these things called gluons, which are sort of the strong nuclear force version of photons. So that's the cartoon picture. Now, neutrons and protons are part of a family of particles known as hadrons. And I'm going to tell you a little bit about how we came to that, the history of how we came to that particular picture there. So by the 1950s, physicists had been doing these wonderful experiments with cloud chambers, looking at tracks of particles curling around. And what they discovered is that by smashing things together and looking at what came out, the debris traveling through the cloud chamber, there was now a bewildering zoo of hadrons. More and more particles kept being discovered, and nobody could figure out how to put order to this zoo. And then in 1961, Murray Gell-Mann and Neyman independently, famously organized this zoo of hadrons because they happened to be a little bit familiar with the representation theory of Lie groups. And in particular, Gell-Mann noticed that the representation theory of SU3 happened to have some structure that very much looked like the structure of the set of known hadrons. And this is what Gell-Mann called the eightfold way. So Gell-Mann wrote this famous paper, which as far as I know, was never actually published, although it's been tremendously influential. And so here is Gell-Mann's famous eightfold way. The neutron and the proton are up there at the top, and it fits into this nice geometric figure with a little pair of different particles sitting at the center there. And Gell-Mann called it the eightfold way because he liked to tell people how he was well read, and he thought this picture looked a little bit like the famous eightfold way in Buddhist teaching, a similar sort of diagram. Of course, the SU3 quickly turned into SU4, SU5, and then SU6 as more hadrons were discovered, and the pictures became successively more complicated. So here are some pictures when you get up to SU4, I believe. And so you can see Gell-Mann's eightfold way is sitting at the bottom of this three-dimensional structure here. And then obviously it gets even more complicated when you get up to SU6. And that 6 is because there are 6 known different types of quarks now. So the implication of Gell-Mann and Neumann's observation was that hadrons have some internal structure. They're made out of these things called quarks that come in different types. And by permuting the different types of quarks, you get these different particles in these diagrams. And that's where the representation theory of these Lie groups came in. And from thinking about this, physicists started to realize that quarks have what's called a color charge, which is like the electric charge that the electron has, except it comes from a 3-dimensional space rather than a 1-dimensional space. Electron charge is +1 or -1, but quarks have a color charge that lives in a 3-dimensional space spanned by basis vectors that you might call red, green, and blue. They have absolutely nothing to do with the colors other than the fact that it's a 3-dimensional space, and people looked around and said, what else do we know in the world that has 3 different descriptors? Oh, colors. Well, that's convenient. Going along with this, the force between quarks is transmitted by these things called gluons, which are photons, except they carry some color charge, whereas photons are electrically uncharged. And what makes things more complicated is that gluons in their basic interactions seem to be able to interact directly with each other, whereas photons have to interact with each other indirectly through electrons and positrons. So by 1965, there'd been a whole flurry of work trying to unravel this picture. And Greenberg, Hahn, and Nambu put together the the final picture, which was a Yang-Mills type quantum field theory where the gauge group was SU3. And this SU3, it's sort of a coincidence that you saw SU3 twice here. This is a different, this is the SU3 corresponding to the color charges, the 3 color charges, rather than the 3 known types of quarks that gave rise to this SU3. So Yang-Mills theory is a system of partial differential equations. And then there's this procedure that physicists like called quantizing it to get the quantum theory. And this leads to what's called quantum chromodynamics, which is the theory, the physical theory that describes the strong nuclear force that puts gluons and quarks together to make things like protons and neutrons and all of these other hadrons appearing in these pictures. So QCD, quantum chromodynamics, is a wonderful theory that has a few issues. One of the issues is that gluons interact with each other, and this is what's called a strongly coupled theory. So the usual perturbation theory calculations that people do with QED, the theory of electromagnetism, they don't work at normal energy scales for QCD. You can't use perturbation theory to get answers to questions. But where we can use it to predict things, it seems to be extremely consistent with theory. But here's here's a picture I was going to show. So the cartoon picture of a proton looks like this. Maybe in light of quantum theory, this is a more realistic representation. You've got 3 quarks and then this cloud of little virtual pairs and gluons zipping around inside there. So the quantum fluctuations make the picture a bit more complicated. Now, there are a couple of problems that you might notice. One of the issues is we said that quarks carry this thing called color charge, and nobody has ever directly observed a particle with a non-zero net color charge. Nobody's ever seen color charge. So this is something we call color confinement. The things that we see are always lumps of quarks and gluons that are put together so that the color charges exactly cancel out and the net charge is 0. We call this color confinement. A special case of this is the fact that we've never seen a quark by itself. We've never seen a single quark, despite all the experiments we've done at places like CERN. So this is what's called quark confinement. And from talking to physicists, I'm not quite sure exactly what the relationship is between these two. Clearly, quark confinement, if quarks have color charge, is a special case of color confinement. One physicist yesterday told me, oh, they're exactly the same thing. And meanwhile, I've seen other papers entire papers that have been written on the relationship between these two. So I'm not quite sure what the relationship is, but there they are. So this idea of confinement, or you can draw some cartoon pictures to kind of illustrate how it works. If you start with a proton, 2 ups and a down quark, and you imagine trying to pull one of those quarks further and further away, you put more and more energy in. And the funny thing about this strong nuclear force is that the attractive force stays roughly constant. So the potential grows linearly with distance instead of the force falling off with distance. And eventually you pull this up quark far enough, and all of that energy that you've put into separating them is able to pull a bunch of junk out of the vacuum in the form of a bunch of other hadrons. These are what are called mesons here, 2 quarks bound together. And a baryon is what you have when you have 3 quarks. In this case, it's another proton. So we've tried to pull an up quark out of the proton, and we ended up instead pulling the up quark out and a whole bunch of other junk that came along for the ride, including another up quark that replaced the one we pulled out. So in the end, our detection apparatus is sitting far enough away from this interaction that all we see is all this junk flying out, which is all bound up in these confined states that have no single quarks and no net color charge. They're all color neutral. So that's all well and good. But then in very high energy collisions, we see evidence that in the moment of collision, this confinement process isn't there. This is something called asymptotic freedom, which was basically everything I've described here has been at least 1 Nobel Prize in physics, if not more than 1. Asymptotic freedom was another one of these Nobel Prizes in physics. So at high energies, we have this phenomenon of asymptotic freedom. The confinement property goes away. And then our detectors are sitting far away from the actual collision. And by the time anything gets there, confinement has taken over. We're back in the low energy regime. So low energy regime, we have confinement. At super high energies, we have asymptotic freedom. And somewhere in the middle, there's something that you might call a transition. And if you put QCD at finite temperature, then maybe this actually is a phase transition in the sense of statistical or quantum statistical mechanics. So QCD has lots of interesting structure. The gauge field here is a connection on a principal SU3 bundle. And these gauge fields can get knotted up in interesting ways. So things called topological objects are things that can appear in the fluctuations or the dynamics of the gauge field. These topological objects are things like vortices, monopoles, instantons, etc. The theory lives on a 4-dimensional space-time, so there's a lot of room for interesting topological objects to appear. And this guy, 't Hooft, who's been really a tremendously influential figure through the development of quantum field theory, and he has been arguing for at least 2 decades now, maybe 3 decades, that this confinement phenomenon that we see at the low temperature, low energy scale of QCD is something to do with these topological objects. And there's this story that it has something to do with a dual picture, which ends up looking a lot like the phenomenon of superconductivity. I don't understand this very well myself, so I'm not going to try to explain it here. But 't Hooft argues this, and then he shows this very convincingly in various toy models that are not real QCD. And yet in real QCD, somehow the argument just hasn't quite been nailed down. So we see relatives of QCD that are simpler, where confinement is driven by some process involving these topological objects. And in real QCD, we don't know what's going on. There are hundreds, perhaps thousands of papers written about this, but nobody has found the smoking gun yet. So there's reason for mathematicians to be interested in this. If you know about the Clay Mathematics Institute and the famous Millennium Problems, Here is one of the problem descriptions. It's called the Yang-Mills and the mass gap. Notice the problem status is unsolved. So this problem is really, to get the $1 million here, it's really two problems that have been rolled together into one. The first problem is to define quantum Yang-Mills theory at a level of rigor that's acceptable to mathematicians, not just physicists. That's an incredibly hard problem that lots of people have been working on since the very beginning of quantum field theory, and we're still not really there. So first you have to define quantum Yang-Mills theory. And then to get the $1 million, you have to go on and do a second thing, which is show that there's a mass gap. Mass gap means that the lightest particle in the theory has non-zero mass. Now the gluons, the naked gluons that you start with when you write down the typical formulation of the theory are massless. And so they should acquire a mass through some mechanism. The states that you can observe should acquire a mass by having, for instance, the gluons tangle around each other into something that's called a glue ball. That's net color 0. So the only way you can have something in net color 0 is if you have a bunch of different gluons stuck together. And that's going to end up having some kinetic energy on the inside, which will be visible on the outside as mass, some kinetic and some potential energy. So to show that there's a mass gap, to show that the lightest particle has non-zero mass, requires essentially to show this process of confinement takes place in the theory. So first you've got to construct the theory mathematically, and then you've got to prove what the physicists still haven't even managed to do, which is that there is some process of confinement going on. So very, very challenging problem if you want to get that $1 million. Currently unsolved. So to try to tackle this, we're not hoping to solve this problem entirely, obviously, but we are hoping to at least suggest some things to look at. If there are topological objects there, that, as Tuft suggests, then topologists should be interested, and maybe we should study it. So we're going to sharpen some tools as topologists and data scientists in a much, much simpler model where we actually already have a full theoretical understanding, so we know exactly what we're looking for. We're going to hone our methods there before trying to tackle some more complicated models, eventually working our way up in the future to something like full QCD. The model we're going to look at is the famous XY model in 2 dimensions. So this is a lot like the Kuramoto model that we heard about yesterday in Ginestra's talk. We have a lattice of sites spread out in the plane. And at each site on this lattice, each vertex, we have a spin, which is some element of the unit circle. So a little arrow pointing in some direction, like the minute hand on a clock. And so the configuration space of the system, the space of possible states, is just a big torus. It's a circle to the number of lattice sites in each direction squared, right? So we have, in this case, we have 16, 4 times 4 lattice sites, so it's 16-dimensional torus. Now you write down a Hamiltonian, which gives you the energy of a particular configuration as a function of the positions of all the spins. And what you do is you put a minus sign in front, and I sum over the dot product of these 2 spins for every adjacent pair of spins. So for each edge, I'm going to take the dot product of these 2 vectors, and I get a contribution, and I sum those all up with a negative sign. That gives me the Hamiltonian for this system. And then we write down what's called the Boltzmann distribution, which is a standard thing in statistical mechanics. So let me just say a few words about this if you're not familiar with this. The idea is we're going to define a probability distribution on this space of configurations here. And I'm going to define this probability distribution by specifying what the probability density function is. So given a state, I need to say what the density function is. And I'm going to write down a function here, this exponential of minus the Hamiltonian divided by some constant times the temperature. That constant there is what's called the Boltzmann constant. So this is the function I write down. And then if it's a probability density function, it has to integrate to 1. So I need some normalization constant in front. So there's the Boltzmann distribution. And then let's think about this for a second, ignoring the normalization constant in front. Sorry, I think I shouldn't have put that psi there. Ignoring the normalization constant, let's just look at this exponential. So if the temperature is very small, then this exponential is dominated by the configurations of very, very low energy. The lowest energy possible dominates the exponential, and everything else is exponentially suppressed. So that tells you that the highest probability states are going to be the ones at the lowest energy. And as you increase the energy by twiddling some of the spins a bit, the probability is going to decrease very quickly. And now that rate of decrease as you increase the energy is controlled by the temperature. And as you make the temperature bigger, then this probability distribution will get smeared out a bit more away from the lowest energy states. There's no time here. This is just a probability distribution. Sorry, somebody's asked a question. Sorry, my L here, so Andrea asks, shouldn't about this L times L. My L is just the number of lattice sites in each direction. So in this picture here, it would be 4 in each direction, so it's 4 times 4. Okay. So the lowest possible energy state is what's called a magnetized state, where all the spins are pointing in the same direction. They're all lined up with each other, so that gives us the lowest possible energy. But then you can also have these interesting configurations like vortices and anti-vortices, where there's a bit of a problem here, a singularity, a high energy contribution in the middle, and where the spins wrap around. And then everywhere far away from that, they try to line up as best they can, and they get pretty close to lining up. Same thing here, but with a winding number of -1 instead. So these are local minima of the Hamiltonian. Now, on a finite lattice, a vortex, obviously, any configuration has finite energy. But on as the lattice size gets larger and larger, it turns out that even though these spins are closely aligned, if you let the lattice size go to infinity, all those not quite perfectly aligned contributions to the energy add up to infinity. So the total energy diverges for a single vortex, and same thing for a single anti-vortex. But something interesting happens if you start with a configuration like this, and you pull a vortex and an anti-vortex apart from each other. So they behave kind of like particle-antiparticle pairs. So they can come together and perfectly cancel out. And oops, when they're, I'm not going to be able to pause that, I think. Let's try to pause it here. So when they're far apart, when there's some finite distance apart from each other, it turns out that even as the lattice size goes to infinity, the total energy contribution now converges. So the divergence from the vortex and the divergence from the anti-vortex just perfectly cancel each other out enough so that the total energy on an infinite lattice is now finite, which I think is an interesting thing. So this is a system that's been very well studied, and it was the result. It resulted in another Nobel Prize. This is the 2016 Nobel Prize in Physics to these 3 guys here. So at low temperatures, what happens is you get vortex-anti-vortex bound pairs. Right? Very, very low energy. You won't even get those. It'll just look more or less magnetized. But you can get these vortex-anti-vortex bound pairs as thermal fluctuations as the temperature starts to creep up from absolute 0. And at very high temperatures, you get such a high density of vortex-anti-vortex pairs that they basically lose track of who's partnered with who. And you get a soup of, sorry, that's vortices, not voices. It's autocorrect doing something there. You get a soup of vortices and anti-vortices dancing around. And in the middle, there's a famous phase transition called the BKT transition that was studied by these guys here. I don't know why Haldane doesn't have his initial on it. And it takes place at a critical temperature of 0.893 approximately. So in the classification of phase transitions, there are first order, second order, and this is what's called an infinite order phase transition. So it's a lot slipperier to try to get a handle on. So now I'm going to come to persistent homology. So the first thing you can do is apply persistent homology in the configuration space. So you can sample the Boltzmann distribution using Monte Carlo methods and get a point cloud in the configuration space. And you can label the point cloud by what temperature the points were sampled from. And then you can try to do something like clustering or persistent homology to try to distinguish the low temperature samples from the high temperature samples from the critical point samples. And this was done by this group of Italians, although I think most of them were actually based in France when they did this. This is from about 5 years ago. And what you see here is I think the red is the persistent homology persistence diagram of the samples they collected from below the critical temperature. The green is right at the critical temperature, or no, sorry, green is below, red is at, and purple is above. And so you can see that the three different persistence diagrams look significantly different. So that's one way of applying persistent homology to study this phase transition. There's a different way of studying this, which is what we've been calling persistent homology as an observable. Now, there are a bunch of papers that do variations on this. When Nick first started working on this project, there was nothing. And we thought this is wide open, and he started working, he started getting some results. And one by one, these other papers started appearing. And so we've had to adapt the project and dig a little bit deeper and think about the contributions of each of these other papers and add something on top of that. So the idea of persistent homology as an observable is we're going to sample the Boltzmann distribution at various temperatures. We're going to get a cloud of points in the configuration space as before. But now we're going to produce a persistence diagram for each configuration. So each configuration of spins is some geometric object, and we're going to convert that into a filtered complex, take its persistent homology, and look at the persistence diagram as a kind of topological fingerprint of that particular configuration. And then we're going to look at the distribution of these persistence diagrams and see if we can learn something about the phase transition from that distribution. So there are lots of different choices of filtrations, and part of the story here is that the choice of filtration matters. So the paper by Tran et al. From the University of Tokyo, they used a filtration. They use a filtration that's, I think I wrote alpha complex, but I think actually they used the Vietors-Rips complex. So what they did is they defined a metric on the lattice that was a linear combination of the lattice distance. So this point here to this point here might be a distance 1. And if you had a point out here, you measure the distance of the lattice to that. So that was one contribution to the metric. And then the other contribution to the metric is the angular distance. So the distance from a point here to a point here would be the lattice distance times some constant plus the angular difference between these two sites times some complementary constant. And then they construct the Vietors-Rips complex. That has the disadvantage of being computationally very expensive if you have a large lattice. The paper by Cole et al. Used a cubical complex with a nicer filtration. And we ended up independently inventing a filtration very similar to theirs, also a filtered cubical complex, because it seemed like a very natural thing to do. So I'll describe ours here. The idea is we're going to let each cell enter at a time proportional to the angular difference. So we start with the full square tiling of the plane, and then we add cells in this filtration when the angular difference is proportional to the time. So if these are 10 degrees apart, at time 10, that edge comes in. These are 45 degrees apart, so at time 45, that comes in. At time 90, these two are 90 degrees apart, so this edge comes in. And at time 125, the last edge comes in. And we, at the same time, we add in the 2 cell there. So that's our filtration of this single, what physicists call a plaquette in this square tiling of the plane. And you extend that to the whole lattice that we're using. Now, this has the effect of capturing some information about vortices and anti-vortices. So here's a vortex here. And early in the filtration, all the stuff that's fairly far away from the vortex will enter because these spins are fairly well aligned. And then the stuff that's a little bit closer to the vortex will enter later because these spins are not quite as well aligned. And then much later at time 90, because these spins are all 90 degrees apart. In fact, these spins, the diagonals are 180 degrees apart. So at time 180, the center will enter. So this filtration will see some persistent cycles corresponding to vortices. So let me tell you about what Tran et al. Did before I tell you what we did. So they did Monte Carlo simulation to extract a set of configurations by sampling the Boltzmann distribution. They construct a set of filtered complexes. They used Vietoris Rips using their metric. They apply persistent homology to get a set of persistence diagrams. And then they used what's called the Fisher kernel to convert this set of persistence diagrams into a finite metric space. So I'm just measuring the distance between persistence diagrams. And then they applied spectral clustering with a number of clusters set to be 2. And what they did is they then looked at how many, at each temperature, how many of the sampled persistence diagrams ended up being in cluster 1 and how many ended up being in cluster 2 or cluster 0 and cluster 1. So at low temperatures, you see that all of the diagrams end up going into cluster 0 and none are in cluster 1. At high temperatures, it's the reverse. Oops, I'm sorry about that. Sorry. I'm paying the price for my fancy animations here. Okay. So at high temperatures, all of the persistence diagrams are going to cluster 1 and none into cluster 0. And at somewhere in the middle, this interesting uncertainty emerges where the clustering is saying I'll put half of these in cluster 0 and half in cluster 1. So the clustering, if you're thinking about it as a classification, it becomes indecisive. It has trouble figuring out if a given persistence diagram should go into cluster 0 or cluster 1. It looks at a diagram and isn't quite sure, is this coming from below the critical temperature or above? We haven't told it that there is a critical temperature, but it's just not sure which cluster to put it in. And so you read that and interpret that as saying, aha, somewhere here where these two things cross over, something's happening. I'm going to say that's the phase transition. And if you look down, that's just about at the right point. So Tran et al. Were very enthusiastic about this. They said this is kind of a universal way of detecting phase a universal machine for detecting phase transitions. And there was a lot of optimism that carried forward from their paper and appears in some of these other papers saying, look at this, we've got this great method that can detect phase transitions. We use a slightly different pipeline, which I'll explain here, to dig a bit deeper here. And I'll tell you now about what we did. So we did Monte Carlo simulation to get a set of configurations. And when I say we, I mean Nick did some fantastic coding work here. We used our filtered cubical complex construction to turn this into a set of filtered complexes, apply persistent homology. And then we vectorize these using persistence images. And maybe that's not strictly necessary the way we ended up doing it, but in order to make a comparison with one of the other papers, that was an appropriate thing to do. So we converted into a set of 2D images, the persistence images. And then we trained a k nearest neighbors classifier with data away from the critical temperature to try to look at a configuration and decide, is it Is it a low temperature ordered configuration or a high temperature disordered configuration? So it's trying to classify it into low temperature or high temperature. And we get this nice plot here. What we're looking at here is the mean of the output of the k-nearest neighbors classifier. So for data coming from the low temperature zone, and the blue indicates where we trained it. At low temperatures, it's very confident that we're in the low temperature regime. And so the mean is close to 0. At high temperatures, the mean is close to 1. It's very confident that's a high temperature configuration. And in the middle, there's this uncertainty. And what we've done here is vary the lattice size. And we've plotted these curves of how certain or uncertain the classifier is along the lines for different lattice sizes, gradually increasing the lattice size to get more and more accurate results. And we interpolate these using what's called a histogram reweighting, which is a standard statistical technique here. And what you see is that there isn't a sharp transition right at this blue line, which would be the critical temperature. Instead is a very soft transition at small lattices. And as the lattice gets larger and larger, it gradually looks more and more like a step function, but it's still smoothed out a bit. And this is the standard behavior that you expect in one of these lattice statistical systems. So if you look at the plot of the variance of the classifier output as a function of temperature, you get a plot that looks like this. Sorry, this is hand-drawn. I didn't have the actual data plot. So at small lattice sizes, you'll get a very smoothed out peak that's fairly far away from where the actual critical temperature is known to be. And as you increase the lattice size, the peak of this curve is going to shift to the left and get higher. So there's some finite size effects that move the peak towards the critical temperature as the lattice size goes to infinity. Here is the persistence diagram. This is the average of the persistence diagrams, just so you can see what it looks like. And you can see that it starts off concentrated in the corner and starts to slide up here. This is in birth persistence coordinates. And then fairly suddenly between 0.8 and 0.95, when we cross this critical temperature, things change quite a bit. And this lump in the corner starts to travel up towards this diagonal line. And the diagonal line is, everything is below the diagonal line because of the way we defined the filtration. So you can see a fairly abrupt change in the persistence diagrams as you cross the threshold of the critical temperature. So let's look more at the finite size scaling effect. This is, in the statistical mechanics physics literature, this is really what physicists pay a lot of attention to. So the true phase transition only happens in the limit when the lattice size goes to infinity. At finite sizes, all of the things that you might expect to diverge are actually smoothed out. So for each lattice size, the critical temperature, the approximate critical temperature, we're going to calculate as the temperature at which the variance of the classifier reaches its peak. So the maximum of the classifier variance, the point where the classifier is maximally unsure about which phase to assign a sample to. So that gives us an estimate for the critical temperature at a finite lattice size. And we're going to use histogram reweighting to get precise estimates of these peaks. And then the statistical theory here tells us that if we have a BKT transition, then the difference between our calculated, from the data, finite size critical temperature and the real critical temperature should scale like one of these functions depending on what type of transition we have. And in the XY model that we're looking at, it's this first one here. In the famous Ising model, it would be the second one. And we use a bootstrap for doing rigorous error estimates here. So here's this picture again. I'll skip over that. So here's the result. Now, one of the papers that came out shortly before ours used logistic regression to do something along these lines, although they didn't look at the finite size scaling effects quite as deeply as we did. We found that logistic regression doesn't actually do very well in terms of calculating the critical temperature and that thing called the critical exponent for the correlation length, nu. So the logistic regression model had some systematic error built into it. It stumbled a bit. Whereas when we use the fully nonlinear model, the k nearest neighbors, things look much nicer, and you see there's some transient effects coming from very small lattices, and as the lattice gets larger and larger, we're looking at these points here, and it lines up very well. And if we continued going, it would continue on this line and extrapolates out to very, very close to where the critical temperature is known to be. We also get a very good estimate of the critical exponent. So the good news is this works for other transitions in the same universality class. So in the theory of statistical mechanics, there's this concept of universality classes, and you can find a whole bunch of different transitions which are all very closely related to each other. They have the same critical exponents that describe these scaling behaviors of different divergent quantities. So for instance, we looked at something called the constrained XY model, which is this funny thing where the Hamiltonian simply assigns 0 if all of the spins that are adjacent are within some threshold of each other, and it assigns infinity otherwise. And then this threshold delta acts like a kind of temperature variable. And this has a BKT type transition at 0.2825 roughly. And same methodology applied to this model gives us also a very good estimate. Let's see, I'm not sure. I'm not sure why I have TC labeled there. I think I might have pasted in the wrong diagram. Yeah, I think I pasted the wrong diagram there. You can see, though, interestingly, the persistence diagrams look fairly different from the ones I showed before. So the persistence diagrams look different, but the method functions in the same way, and you can extract the same information to roughly the same accuracy for the BKT transition in this variation of the XY model. The paper by Biagio et al. Said, well, let's take this sort of realm of methodology, and let's look at a model that has lots of phases, not just one phase transition. So they looked at the XXZ model on a 3D pyrochlore lattice, which is some complicated lattice, which I won't draw, I don't have a picture of here. And what they did is same sort of pipeline. They used the sliced Wasserstein distance between persistence diagrams. And then once they have this finite metric space, they said, well, let's use MDS to reduce it down to 3 dimensions, and we'll picture the 3 dimensions as color space. And so at each point in the phase diagram here, we can plot a color, and superimposed over this is black lines showing theoretically where the known phase boundaries are, where the phase boundaries are known to lie. So this has 6 different phases, and you can see that these different color patches more or less correspond to the different phase regions. So this is looking fantastic. There is a kind of growing sense of euphoria in the literature here. We've got this method that can pick out all sorts of different phases completely agnostically. You don't need to know the details of what's going on in the transition. You don't need to have a priori theoretical knowledge. You can discover something this way. So we came along and said, well, let's study this a bit more carefully. And well, I have to give Nick credit here again. He found this thing called the nematic XY model, which is like the XY model, except you add a second term to the Hamiltonian. So here's the first term we had before, which favors these spins to be aligned. And then you add this second term, which also likes the spins to be anti-aligned, so simply by sticking a 2 in there. And so we've got this parameter delta that controls the balance between the 2 terms in the Hamiltonian. And for the moment, in the work we did, we fixed it at 0.15, but I'll show you the phase diagram in full in a second. And now, as you increase the temperature, you have two phase transitions. There's the familiar BKT transition, like in the XY model at this temperature here. And then there's also an Ising model type second order transition at a lower temperature. There we go. So we have low temperature, there's a ferromagnetic phase. In the middle, there's a pneumatic phase. And in the high temperature region, there's a disordered phase. So this pneumatic phase is what's new in the pneumatic model. So we've got two phase transitions. Let's see if we can do something like what Biagio et al. Did and see both of these simultaneously. Here's the phase diagram. This is from 1989. I thought this is pretty cool that I used a computer in 1989 and they were not fast back then. So it's amazing that they were able to do the numerical work to construct this phase diagram. We're looking at sweeping along this vertical line here that's in the temperature direction. So we're going to cross one phase boundary and then a second one. So the interesting thing with the pneumatic model is you can get these, you can get half vortices, which are connected by these domain walls. So this is an interesting new phenomenon. In the ferromagnetic phase at low temperatures, things tend to align. When you go into the pneumatic phase, you get lots of these tubes appearing, these little domain walls. And then you go to the high temperature disordered phase, and these start to break apart. When we look at the persistence diagrams using the same methodology, you see here, there's no visible evidence of any sudden change in the persistence diagram where we expect that second order transition to be occurring between 0.25 and 0.4 temperature. You just don't see it there. And we didn't just stop by looking at the picture, we actually did the analysis and saw that this filtration in this method doesn't see that, that transition. So I realize I'm just about out of time. I'll just say fairly quickly here. The solution to this is you need to go back and choose your filtration very carefully. And this is a point that we really want to make, which I think has been overlooked in some of the previous literature. The filtration you use has to really be tuned carefully to the transition that you're trying to detect. So we used an adapted filtration, we call it the pneumatic filtration. And just to show you here, even though these are anti-aligned by 90 degrees, 180 degrees, what am I doing there? These are 180 degrees apart. We bring this edge in first because in the pneumatic filtration, those count as the same. And then we bring the rest in. So these are closely aligned. These are a little bit less closely aligned. And then down here, this comes in at time 55 and we fill in the square. So in the normal filtration, we have this picture. In the pneumatic filtration, as you transition from here to here, you see, you now see a fairly abrupt change. There's the stuff in the corner, and then this stuff in the lower right corner starts to appear. So the pneumatic filtration sees it sees the second order transition from ferromagnetic to pneumatic phases, but it doesn't see going from here to here, it doesn't see much about the BKT transition, whereas the normal filtration was the reverse. So we have one filtration for each of these two transitions, and we don't have a filtration that sees them both simultaneously. So I'll just end with my conclusion there. In the 2D XY model and some relatives, we went beyond simple phase indicators. We went beyond simply saying, oh, we can see that there are two different phases there. And we made precision numerical measurements of the critical temperature and the critical, at least one of the critical exponents. We're not quite at the level of state-of-the-art measurements of these quantities because the state-of-the-art measurements require going to much, much higher lattices still and running the computer for possibly weeks. But this is a kind of proof of concept that we're competitive just by using this persistent homology method. Including in this, we did rigorous error estimates using Bootstrap, so you can really see how good your estimate is. And the take-home point is that the filtration has to be adapted to the topological objects that you're studying. So if we want to study QCD, we need to think very carefully about which topological objects are there and how we're going to see them with a filtration. So I'll end there. Thank you very much.
Thank you, Jeff. Let's thank Jeff, please.